From last Friday to this Wednesday, we have already learned the lumped composite method. And which assume the temperature distribution is uniform inside our defined control volume. And we learned some dimensional number, which termed Biot number, given by the ratio of convection transfer coefficient times some characteristic length over the thermal conductivity of the solid material. And we learned by Wednesday, if it's much smaller than 1, then we can assume everything is uniform in the center, in the surface. Every point inside the object has the same temperature evolution. Now today, that's the easy way to calculate the temperature evolution. But in many engineering problems, the Biot number is not always much smaller than 1. We are going to figure out a different example with a much larger Biot number and apply different approach to study how the temperature distributes and how it evolves with time. Let's say consider a sphere, but instead of copper, it's made of coal now. Let's say an anthracite coal sphere has the same diameter of our copper example, which is 6 centimeters. But with a much less smaller thermal conductivity, which is 0.26 watt per meter Kelvin. Instead of putting it into the still air, we now put it into flowing water, and it has a much higher convection coefficient. For moving water, the convection coefficient is 1,000 watt per square meter Kelvin. At the very beginning, everything inside the cold sphere is at 90 degrees, and the temperature of the moving water, 20 degrees. Now, my question here is, how can we calculate the evolution of its temperature distribution as a function of both the spatial variable and the change in how it evaluates with time? Very similar to our copper sphere example, but now with a different material. What should be our first step to solve a transient conduction problem? Because the temperature distribution now depends with the time. It's a transient. Right. If we want to take the easy way out, consider everything has the same temperature distribution. But to apply the lumped composite method, let's check whether or not we can use it with reasonable accuracy. Biot number calculated as HL over K. Now plug in the convection coefficient and for sphere, the thermal heat transfer characteristic length is simply given by its radius, which is 3 centimeters over the thermal conductivity of the coal sphere, 0.26 watt per meter Kelvin. We end up with 150. For sphere, the copper sphere example, the Biot number is 7.5 up 10 up minus 4th. But for this coal sphere, because it has such a different material property and immersed in moving water with a much intense convection coefficient, we have a much higher Biot number, which is, in general, we can say it's much larger than 1. What does this result tell us? We get a much large Biot number. Exactly. Can we still assume the temperature distribution inside the core sphere is uniform? No, we can't. Because Biot number, we learned this thing on Wednesday, can be an indicator of the ratio of internal gradient to the temperature difference of the outside temperature difference. Now, with a high Biot number, which means the internal temperature difference cannot be neglected. We can let's draw how the temperature profile. The same the sphere with a diameter of 6 centimeters and immersed in moving water of 20 degrees and 1,000 watt per square meter Kelvin for convection heat transfer coefficient. Let's say we would like to know how temperature distribute across this line AA and we mark everything we know and designate its radius as L. At the very beginning, everything stays at the initial temperature, which is 90 degrees. And we know by the very end, everything inside the core sphere reaches the same temperature as that of the water. But that's for the cooling. Instead of consider the cooling process right after it gets immersed in the water, let's consider how the temperature distributes in the intermediate stage. For this case, this is for after a short period of time of cooling, we can say after some characteristic time. Let's consider this case first. What will be our temperature distribution look like? Consider this case after a period of time. Let's consider the center temperature first. After a short period of time, what will be our center temperature? Should be still at the T0? No, it's a cooling case. So somewhere intermediate. How about surface temperature? A little bit up. Let's say something here. That's our surface temperature. Because we have it gets immersed in the moving water with a much higher convection coefficient. After a period of time, the surface gets cooled down very quickly, and we can say it can be reach the temperature of the moving fluid. What should be the slope at in the center of the sphere? Any value other than 0 will break its spherical symmetry. So we always have 0 slope here. The temperature profile looks like parabolic or like a cosine function, but we will exactly know the exact distribution after reading week. And let's consider the initial stage. At exactly temperature equals 0, the time equals 0, everything stays at the initial temperature, T0. Then what happens shortly after the cooling process starts? Let's consider separately. How about the center temperature? Yes, because consider a very short period of time. The center does not realize what happened outside, still remained as its initial temperature. But how about the surface, which is directly exposed to the moving water, a little bit cooled down? Exactly. Say after it will have some shape of profile like this. We say T at the point T equal T1, but still shortly after the cooling process. With increasing time, the surface temperature keeps decreasing. You see, this is T equal T2 until what? You see, now at this stage, the center has no idea what is going on outside. The cooling process only cools the surface temperature for now. So the surface temperature decreases until it reaches that of the fluid temperature. So we call this stage stage 1. From T exactly T0 to T3. In this stage, the cooling fluid only cools down the surface. And until the surface temperature reaches the same temperature as that of the cooling fluid. Then after that, if the time increase in this direction, after that, what will be our temperature profile look like? As you see, the center and the vicinity of the center, still the profile will get penetrate. Until the heat reaches the center. This is at the time T4, and we call the time for the heat reach the center at T equal T5. It still takes some time for the heat to transfer until it reaches the center of the sphere. We call this stage 2. In this stage, surface temperature maintains T infinity, but the profile penetrates until it gets to the center. Because we have a very large Biot number here with moving water, I figured out the example. When we try to cool down the boiled egg, we would like to remove the shell. We put it into the running water. Then it makes it easier to remove the shell after we expose that into the running water. But the inside, the yolk of the egg is still very hot, although the surface gets cooled down, which means it takes time. Just like this example, it takes time for heat to penetrate into the center. The surface is already cooled down, but the center needs some time to realize what happens. And then after it realizes, after heat penetrates into the center, then after that, the center starts to get cooled down. The slope at the center by symmetry should always be 0. So for T6 to T8, we call those stage 3. And that's the evolution of the center, for the temperature of center to get decreased. And this case only applies for built number, which is much larger than 1. Because if much smaller than 1, the temperature difference between center temperature and the surface temperature is negligible. Only for built number larger than 1, then we have a much complex process here. Any question about this curve? We involve zero mass here, just build the qualitative curves based on our intuition to understand what happens on the surface, and then for the heat penetrates into the center, then center gets cooled down. Now, if I pick I would like to know how temperature changes with time for our center and how the temperature evolves for our surface temperature. Let's consider surface temperature first. We draw the temperature evolution. It means we pick a fixed point in the sphere. We pick, let's say, surface temperature now, and draw how the temperature change varies with time. For temperature profile or distribution, that's how temperature varies with space. We pick a fixed time. That's short after cooling, after a short period of time, and to describe how temperature varies in space. So those curves are essentially equivalent. We should be to understand and jump easily from each other. Let's consider surface temperature now. We mark everything we know at the beginning, everything at the T0. After a long period of time, everything reaches the same temperature as T infinity. Now, for our surface temperature, what should be its temperature evolution? How it varies with time? Exactly, it will get cooled down really quickly, and then maintains at the temperature of that, as it shows in. That's our stage 1, from T1 to T3. The surface temperature gets cooled down by the intense convective cooling. Now, how about center temperature? The blue point here. It keeps flat for a period of time. Until what? Should it be a horizontal line always? No. Because we know at the very end, everything should be cooled down at the temperature of infinity. Then what happens next for our center? You see here, at the beginning, it does not realize what happens until what? Until stage 3. Yes, until heat penetrated into the center, and then it will decrease and reach the T infinity after a period of time. So the stage it still remains as the initial temperature. We call it stage 2. And because at this stage we see the surface temperature, the surface already cooled down and maintains the same temperature as the fluid, but the center, it takes time for heat to penetrate into the center. That's our stage 2. And after that, that's the cooling of our center. That's stage 3. And the blue curve, this is our T center. But this curve, just as Dr. Manner said, only valid for built number much larger than 1. We have easy case, built number much smaller than 1. And now we work on another easier case, build number much larger than 1, but we still have something else in between. Then we will figure out that later.